Okay, so welcome everyone to another session of the algebraic geometry seminar. Today we are very happy to have Ryo Yamagishi, so from University of Bath. So he used to be a postdoc at the NTU, so and went to UK last April, and then he's visited here for 1 week, and his office is in the other building, so the Astromass building, 5th floor. 529, I think. Yeah, so if you want to discuss with him, then he will be available in fifth floor for the whole week. Yeah, so today he's going to talk about Hilbert schemes of points on canonical surfaces. Yeah, please.
Thank you for introduction, and I'd like to thank the organizer, Issuing Online, for invitation to algebraic geometry seminar. So, okay, so today I'd like to talk about Hilbert schemes of points on surfaces. So let's start with the definition of Hilbert schemes of points. So basically, in this talk, we only consider surfaces. So let S be a quasi-projective connected surface. Defined over the complex number field. So basically, almost all results hold for any algebraically closed field of characteristic 0, but just for simplicity, we work over the complex number field. Yeah. But this is not essential. So basically, all the results hold for any, at least for any field of characteristic 0. So anyway, so for this surface, we consider the Hilbert scheme of points on S. So as I said, this is the set of closed subschemes of S such that the coordinate ring of this subscheme has dimension n as a C-vector space. So this is a subscheme, so it may be non-reduced, and especially each subscheme might have just one point as a support. So anyway, so this is, as I said, this is set of subschemes, and in fact, this has a natural scheme structure, and so in fact, this is a quasi-projective scheme, Noetherian scheme, defined over the complex number field, and so this is so this is the Hilbert scheme of points.
Maybe OS should be OZ, and then Z should be 0.
Oh, sorry,
and Z should be 0 dimensional.
But
because if S is projective, then if Z is
I see.
yeah.
Okay.
So dimension Z.
There's dimensional, yeah. Good. And okay, so this is the Hilbert scheme of endpoints. Yes. So the aim of this talk is to give a generalization of the famous result by Fogarty. So maybe okay. So the theorem by Fogarty is stated as follows. Fogarty. This result was published in 1968. So the statement is as follows. So if S is a smooth surface, then the scheme here n S here n over S is a smooth variety of dimension 2n. So if S is non-singular, so the Hilbert scheme has the same property, so it is smooth, and it has the expected dimension 2n. But in general, it's very hard to study the geometric structure of the Hilbert scheme of points. So, for example, okay. Before that, let me state the main result of this. So basically, the main theorem of this talk is to generalize this result to mildly singular surfaces. So the statement, the statement is the following. So if S is a normal surface, so here we assume this is mildly singular surface with only canonical singularities. So, so now it is surface, so this is equivalent to having AD singularity. So, then the corresponding Hilbert scheme, Hilbert n of S, is a normal variety of dimension 2n. So similarly to this theorem, so if S has relatively mild singularities, then the corresponding Hilbert scheme also has a similar property. It is a normal variety of, and it has the expected dimension 2n. But so let me give some remarks. So you might expect that if S is irreducible, so the Hilbert scheme is always irreducible, but this is not true. So for example, there's some result. So if S is more singular, then S can be reducible. So even if S is a normal surface, then the Hilbert scheme can be reducible. So usually it's very hard to control the singularity of the Hilbert scheme of points. And also for higher dimensions, so even if the original variety is smooth, the Hilbert scheme can be again reducible. For higher dimensions. And for sufficiently large n. So compared to these two cases, so the case where S has only canonical singularities, then the silver stream has much nicer singularity. So, okay, so maybe change the blackboard.
So it's the theorem optimal. So if you allow like low canonical singularity.
Yeah, I think for low canonical singularities, this silver scheme can be reducible. Yeah. So,
Reducible means this joint components or the
the Hilbert scheme is if the surface is connected, then the Hilbert scheme is always connected. So the components should intersect. So, okay. So let me explain the rough strategy of the proof of this main result. Strategy of proof. This is threefold. So basically, in sorry, greater than 2. So the example for three-fourths. I don't explicit idea. So, yeah, I think so. We still don't know the exact value for of n for this Hilbert scheme to be reducible. So even determining the value is difficult problems. Basically, knowing the structure of the Hilbert scheme is difficult for especially for singular variety and higher dimensional varieties. So there are mainly two parts for the strategy of the proof. So the first part is to show that the Hilbert scheme of points of certain specific singularity, the finite quotient of a two-dimensional vector space by a subgroup. So this is gamma is a subgroup of SL2. So this is finite subgroup. For this specific surface singularity, we show that the Hilbert scheme is isomorphic to a certain Nakajima Kiva variety. So later I will give the precise definition of this variety. And by a general result, we know that this variety is normal, irreducible, and so on. So for this specific singularity, we can show that the Hilbert scheme is satisfies this condition. Yeah. So this is normal and irreducible, reduced, and have the expected dimension to it. And as the second step, show that the singularity of Hilbert, the Hilbert scheme of the surface is depends only on the singularity of S. So here, the singularity means the analytic local singularity. So, or if we consider the more general algebraically closed field of characteristic zero, so this is a eta local neighborhood of the single point, and so in fact we can show that this Hilbert schemes depends only on the analytic germ of the singularity of the original surface. Yes. So in this way we can prove this main result. Okay, so in fact, so in this talk we will mainly focus on the first part. So in fact, so we will show that we will see that this Hilbert scheme is in fact realized at certain modular space of Kuiper representations, and the Nakajima Kuiper variety is also a modular space of Kuiper representations, and so we can compare these two modular spaces, and finally we can identify these two things. And if time permits, I will also briefly explain the second step of the proof. So next, I want to give a description of the Hilbert scheme of points on the surface as certain Kuiper modular space. Sorry, so here we consider C2 mod gamma rather than a general surfaces. Depends on of course, yes. So more precisely, S and the number. Yes, sorry. Thank you for pointing out. So this quotient variety is realized as certain hypersurface. So there's some polynomial H gamma in 3 variables, y and z. And in this case, and we call this ring R. And we also consider that Kuiper, maybe. So we realize this Hilbert scheme as certain modular space representations of a certain Kuiper. So here we consider the following diagram of C vector space and linear maps. And here we consider three endomorphisms. So we call these endomorphisms B1, B2, and B3. So in fact, this Hilbert scheme is realized as a modular space by the following fact. So this is due to Crow, Gamma Gold, Genge, and Stendroys. The Hilbert scheme of points on C2 mod gamma is isomorphic to the following space. So quadruple of C linear maps. So either C linear map from C to Cn and B1, B2, B3 are endomorphisms of Cn, such that they satisfy the following conditions. The first condition says that each BI commits with each other, so this is 0 for any I and j. And the second condition says that the H gamma, so this is the defining equation of the singularity. So if we substitute B1, B2, B3 to that polynomial, this should be 0. And finally, okay, so the third condition is the following. The set of, sorry. Here R is just the polynomial ring in 3 variables. Generate the whole space Cn. Here, 1 is just a complex number, and so the third condition requires that the image of 1 under this linear map I generate, and so if we apply these endomorphisms, then they generate the whole space Cn. So in other words, any Kuiper subrepresentation containing the image of 1 is equal to the whole representation. And we should also take the quotient by the action of GLN. Here, this GLN acts on this vector space by conjugation. Okay. So this space has a natural scheme structure, and in fact, this is a isomorphism as schemes, not just sets. Okay. And the precise correspondence is given as follows. So for each quadruple I, B1, B2, and B3, we can equip the R module structure on Cn. So more precisely, so for each given these linear maps, we can consider the ring homomorphism from R to NCN. So namely, so for each variable x, y, and z, we can assign B1, B2, and B3. So the first two conditions correspond to the well-definedness of this ring homomorphism. So for this ring homomorphism to be well-defined, these variables should be commutative, and also, so this is a sorry, sorry. もちろん I あと1ガンマ should be commutative, and also we need this second condition for this to be well defined. And then
So do we need to choose a stability condition to define the portion?
Yeah. So in fact, the third condition corresponds to the stability condition. So more precisely, for given this data, we have a surjective ring homomorphism from this quotient ring to Cn. So this is algebra morphism and okay, so R means R linear maps. Okay, so we can take the kernel of this surjection. Then we get how to say so. We get the corresponding Kurosawa spectrum of the so H plus. So this is the correspondence. So you can easily check that this gives a one-to-one correspondence of the both sides. And we need to quotient out by GLN action. So next, I will introduce the notion of Nakajima-Kuiva varieties. And I will also explain the related bilateral geometry. Of this variety. So, Nakajima-Kuiva variety is also a modular space of certain Kuiva representations, and it has a natural symplectic structure. And so, in fact, so finally we will show that this is out of that Hilbert scheme is out of the Nakajima-Kuiva variety, and also so in fact the minimal resolution of the C2 mod gamma. So the Hilbert scheme of points on the minimal resolution is also realized as a Nakajima-Kuiva variety. So before going to general situations, let's consider the two-dimensional example. So first, let's consider the affine Dynkin-Kuiva. This is Cn. So by definition of the Hilbert scheme, the quotient must be n-dimensional C-vector space. So in some sense, this construction gives the module structure over this ring on the n-dimensional vector space. So in some sense, this is the modular space of R module structures over this ring. Then we can identify this modular space as the modular space of ideals or subschemes. Okay. Yes. So here we consider the finding Kuiva for corresponding to the gamma, so the final subgroup of SL2. So maybe here. So for example, if gamma is of type D5, the Kuiva Q gamma is the following. So this is the usual linking diagram of type D5, and the affine Dinky quiver is obtained by, and also, so if we add one edge and one vertex, so basically I should say that the vertex set of this quiver is the set of irreducible representations of gamma. And so if we remove this one, this is the usual thinking diagram. And when we consider affine thinking diagram, we need to add one extra vertex, rho 0, corresponding to the trivial representation. And to get this quiver, so we introduce 2 arrows for each edge of the thinking diagram in the other directions, so like this. So this is the thinking quiver, affine thinking quiver for type D5. And we will consider modular space of quiver representations for this quiver. For this, we also introduce the dimension vector delta. The dimension vector is defined as the dimensions of the corresponding irreducible representations, like this. So this is just tuples of n plus 1 tuples of natural numbers. And also, we also consider relations for this quiver. So in this case, the relation is given as follows. So we consider the algebra pi gamma. So this is the non-commutative algebra. This is the quotient of the path algebra modulo sum ideal. So this is the so-called projective algebra. Okay. Okay. So basically, so this CQ is just path algebra, and I gamma is generate the idea of relations for this quiver. So in this case, so if we write arrows A1, A2, A3, A4, A5, and A6, and so on, then this idea is generated by the following elements. So for each vertex, we consider all the cycles of length 2. So for example, for this vertex, the corresponding relation is A to A1. And for this vertex, A3, A4, A3. And for this vertex, we consider all the cycles of length 2 with certain signs. So in this case, A1, 2, minus A3, A4, plus A5, A6, and so on. So this is the definition of the projective algebra. So basically, we will consider modular space of quiver representations satisfying these relations. Okay, and we also consider the group action on the space of quiver representations. So here we define G delta as the product of GLN, GL delta K. Okay, so as here, the delta k is the same as the dimension of rho k.
Sorry, how to define decide the sign of
I think the sign is not essential. So for any, how to say, yeah, there's a certain rule, but I forget the precise rule for how to decide the sign. But I don't think this is essential. Even if we change the signs, we can produce isomorphic varieties. Probably, so maybe it's not correct. Okay, and so here we consider the group G delta. This is the product of GL delta K. And we take the quotient by one-dimensional subgroup because this subgroup acts trivially on the space of representations with relations pi gamma delta. Yeah. So if we take the quotient, then this group acts effectively on this space of representations. Okay. So in order to define the modular space, we also need to introduce the notion of stability conditions. So basically, so this is the space of stability conditions introduced by Alastair King. So basically, this is just a group of characters of the acting group. So in this case, G delta. With coefficients in real numbers. So in this case, this is just the set of tuples of real numbers such that this this equation is satisfied. Maybe K. This condition corresponds to taking the quotient by this one-dimensional subspace. So basically, the character group of the quotient corresponds to subspace of the character group of the original group, the product of GL delta K. So now we can define the modular space for any element here. We can define the m theta pi gamma delta. By definition, this is the geometric invariance theory quotient by the action of G delta with respect to the character or the stability condition theta be the modular space introduced by King. In fact, there's a representation theoretic characterization of stability condition, but here, let me omit the details. So anyway, so we can construct a modular space of representations as a certain GAT quotient. So, so now we can state the following result by Kronheimer. in 1989. So for generic stability condition theta, so in general, the space of stability conditions has a wall and chamber structures. And if we take a element from a chamber, then we can construct the modular space and the natural morphism. From the modular space for generic stability condition to the modular space with the corresponding to the trivial stability condition. So this is always affine. Is identified with the minimal resolution. Minimal resolution of the quotient singularity. So in this way, we can construct a resolution of singularity as a modular space of this kind of paper representations. So in fact, originally the result of Kronheimer was in his result, the modular space was constructed as a hyperkähler quotient rather than the GIT quotient, but they can be identified. So anyway, so we can construct this. We construct the minimal resolution as a modular space in this way. And in fact, we can also construct the Hilbert scheme of points on this singular variety and also the Hilbert scheme of points on this Sims variety as Nakajima-Kuiper varieties. And before giving the construction, so let me explain the how to say birational geometric viewpoint. So in fact, we will show that so there exists the following diagram. So in general, if we have a Hilbert scheme of points on any scheme, we can define the Hilbert-Chow morphism to the symmetric power of the scheme. So in this case, we consider C2 mod gamma. So this is the Hilbert-Chow morphism. And this is the symmetric power. So by definition, this is the product of n copies of this quotient variety modulo the action, the permutation of the symmetric group. And also, since taking the symmetric power is functorial, so we also have the symmetric power of the minimal resolution of this AD singularity. So we have a regular morphism from here to here, and we can also consider the Hilbert-Chow morphism from the Hilbert scheme of endpoints on the minimum resolution. So this is smooth, so the Hilbert scheme of point is smooth by the result of Fogarty. And in fact, this is also, it also has a symplectic structure. So this is in fact smooth and symplectic. So this gives in fact, this gives a symplectic resolution of these two varieties. But we don't have any usually we don't have a morphism from here to here because taking the Hilbert scheme is not factorials. But if we apply certain operations, so-called flops, we get another symplectic manifold X, and also we have a regular morphism. So in fact, this is also smooth and symplectic. Okay. I'm going to later I'll give more detailed explanation for this diagram. Okay, so in fact, all these varieties are realized as Nakajima-Kruger varieties, and now I'll explain the construction, the general construction. Okay. So in order to construct, maybe in order to construct Kruger varieties for these varieties, so we modified this quiver. So we change the color. So we introduce a new extra vertex here. This is often called labeled by infinity, and we also consider two arrows in the other directions, and also okay. Corresponding representation, what?
Each point vertex of the
Ah,
the first infinity of
I don't know a good interpretation of this vertex, but basically, the number of vertices is the same as the Picard number of the resolution. So, and in fact, for these two symplectic resolutions, they have the same number of exceptional divisors as the number of vertices here. So they have the Picard number of the resolutions is equal to the the number of vertices without the infinite vertex. So in some sense, so these vertices correspond to exceptional curves of the minimal resolution of system bot gamma, and this vertex corresponds to the how to say? So, no, corresponds to the exceptional divisor for the Hilbertian morphism. So this has the difference of the Picard number is 1. So this has one exceptional divisor, and maybe we can say that this vertex corresponds to this exceptional divisor. Okay. But I don't know a good interpretation for the correspondence of vertices and exceptional divisors. Okay. And so here now we consider this new quiver. So we denote this new quiver by Q gamma tilde, and we also consider the corresponding group projective algebra pi gamma tilde. So this is basically the projective algebra for Q gamma tilde. Then similarly to the Kroneheimers construction, we can construct homogeneous space. So, and in this case, we consider the group G in delta. Before that, we introduced the dimension vector and delta tilde. This is consists of 1 and n delta. The first entry corresponds to this extra vertex, and for the other vertices, we consider the n multiple of delta. So this is n plus 2 tuple of natural numbers. And we also consider the group G delta, Gn delta. By definition, this is the product of GL and delta K. But in this case, we don't take the quotient by this one-dimensional subgroup. So this acts on the space of representations for this algebra. Delta tilde. Here we don't take the quotient because this one-dimensional subgroup does not act trivially on this representation space. Okay. And similarly to the two-dimensional case, we introduce the space of stability conditions. So this is just the character group of this acting group. So this is n plus one dimensional R vector space.
Sometimes at the infinity vertex is some kind of branch cover and cover of the cohesion moduli. Right?
Cover?
And branch cover, data cover.
I don't think so. Yeah. Okay. Maybe. Maybe we should use that part. Okay, what is larger than? K is the index of representations, and N is independent of the choice of K. So, what do you?
Yes, the question is index K should be 0, 1 to m and then infinity, not up to infinity. Just m plus 2 copies, not infinity copies.
Not infinite copies. You have to.
I mean index, but index is only running from 0, 1 to up to m and then jump to infinity.
Here.
I'm sorry.
Yeah, sorry, here I. Okay. No, I. Sorry.
There is no delta of k plus one.
Only infinity, then infinity is one.
So the dimension vector here is 1.
Only that.
Okay. Maybe I erased. Okay, okay, sorry. Okay, so here, that's the reason. Okay, so I raised the delta tilde is 1 and delta, and sorry, I erased the and okay, so now we can and so I should write here. So this is R plus one dimensional vector space, and then in fact, so all the I'm so sorry, I used the diagrams. All the varieties in the diagram can be realized as the module space has the Nakajima variety. So this is Bellamy and Co. So all project symplectic resolutions of symmetric power of the edge singularity are obtained as the module space, and then for this quiver and these relations, pi gamma and delta tilde to the affine module space. Okay. For generic stability condition. Maybe I should write it again for feet and seat and him. Plane. So in fact, we can say more about the structure of resolutions. So let's see some example. So here we consider the case where n is equal to 3. So here we scheme of 3 points for edge singularity of type A2. So in this case, the stability condition has dimension 3. And so inside this vector space, there's certain convex cone like this. So this is a slice of three-dimensional convex cone. So we have, and so, and inside this cone there are modern GIT chambers. So this cone is divided into chambers. Like this, and we also have. And in fact, okay. So this theorem especially implies that the modular space for the trivial character is isomorphic to the symmetric power of theta mod gamma. But this was originally due to Crowley Booby. And there are many chambers, GT chambers, but among them there's some special distinguished chambers, C minus and C plus. In fact, the modular space for C minus is isomorphic to the Hilbert scheme of endpoints on the minimal resolution of the AD singularity, or a type A2 singularity, and the MC plus is isomorphic to this resolution X. So in fact, this is usually called N gamma Hilbert scheme on C2. So this is also a kind of Hilbert scheme, but I don't explain the detail. But this has some interpretation as a kind of Hilbert scheme. So these varieties are studied by Hyman, Kuznetsov, and also Nakajima.
Tension N gamma in some sense is some kind of N copy of gamma.
Yeah.
with small modification.
Yeah, so the definition is that this is the set of subschemes of C2, which is isomorphic to the direct sum of n copies of gamma as a modulo over gamma. Yeah. Okay. So
Oh, so is it the same as the G Hilbert scheme of C2n, with G is the maybe semi-direct product of Sn with
yeah, I think so. Probably, yeah. I'm very confident. Maybe yeah, you should check. So this has interpretation as a Hilbert scheme, and also, so for example, if we take an element from this world, then the corresponding modular space is this symmetric power of the minimal resolution, and so here we need flops, and the flops correspond to wall crossings. So the set of chambers inside this cone is in one-to-one correspondence with the set of all projective symplectic resolutions of this symmetric power of this AD singularity. And here there's also some special stability condition theta plus. Here this is written explicitly like this. So okay, so okay, maybe. So we can prove the main result by proving the following claim. So the modular space for this stability condition is isomorphic to the Hilbert scheme of endpoints on C2 mod gamma. So if we can prove this Hilbert scheme fits into this part of this diagram, and also by a general result, this is a normal reducible variety, so we can prove the main result for this specific surface singularity. So in order to prove this claim, we need to, okay. Okay, so to prove this, the following result. Play the key role. The following result is a very general result for Quiver representations. So the statement is the following. So first consider any Quiver Q. And we also fix any dimension vector B. Q0 is the vertex set of the quiver, and so this is element of NQ0. So this is the dimension vector, and we also consider any subset K of the vertex set of Q. We define a group HK as just the product of GL and BK. So this acts on the space of representations of the quiver Q with dimension vector B by conjugation, the change of basis. Okay. Then the invariant subring of the coordinate ring of the space of representations. With respect to the action of HK is generated by the following two types of generators. Okay, so generated by the first type generator is the following. So the trace associated to cycles gamma. So as a function on this representation space, so if we consider a representation of QB, so this is just a set of collection of linear maps. So this is the element of the representation space. So for each representation, we assign to it a trace of matrix product. Okay. EL for cycles gamma in Q such that each AI has and tail in K. So we can check that this function is invariant with respect to the action of HK. And also, we should also consider the following function, xpij. So this is similar to the first one. For each given representation, we consider the, the ij entry of this matrix product. So this is means just the ij entry of the matrix for path. So in the first case, we only consider cycles, but here we consider more generally paths. Thank you. Such that the path P has head and tail in the complement of K. So, sorry for small letters. So you can also check that this function is also invariant with respect to the action of HK. So this theorem plays an important role in the proof of this isomorphism.
So you don't assume that head and the tail of P
Mhm.
each a segment, just P. The endpoint and starting from P only,
Mhm.
not AI, not.
So
Last line is what?
also the meaning is that the head of path is just the head of the last one. Mm. Okay, so let me give some remarks about that theorem. So let's consider two extreme cases. So if K is empty, then the claim is trivial or claim is trivial or obvious. Because so in this case, HK is trivial, so this is just the space of all the coordinate ring of all representations. So of course, this is generated by all the entries of the matrix, and if it's the whole vertex set, then this theorem covers the classical De Broglie approaches theorem. So the De Broglie approaches theorem states that so if HK is if K is the whole vertex set, then the invariant ring is generated by traces of the cycles. So we can recover this result by other special case of that theorem. So, okay. Now we can give a rough outline of the proof of this isomorphism. Okay. So to prove this isomorphism, we first consider the modular space, another modular space. So, so instead of pi gamma tilde, we consider new algebra A with the same dimension vector delta tilde. So here, okay. Here we define the algebra A as just the quotient of gamma pi gamma tilde modulo the ideal generated by B star. We call these arrows B and B star. So in this algebra, we remove this arrow B star. Okay. So then this modular space is regarded as a subscheme of this modular space, and later we can see that in fact this closed subscheme is in fact the whole thing. So
So it's some kind of disjunction of what is it called, free product of actual parameter. Because there is no cycle through infinity, so sometimes isolated.
yeah. So the reason why we introduce this algebra is to consider cycles only involving the right-hand side. So if we have these arrows here, this infinite vertex are also involved. So to prove this isomorphism, we first show that this modular space is isomorphic to this Hilbert scheme. So in order to apply the result here, we set K from row 1 to row n. So in other words, this is the complement of Q gamma tilde, complement of the infinite vertex and the vertex corresponding to the trivial representation. And also consider the corresponding group HK. So in this case, this is the product of K from 1 to n, GL, and delta K. And so we will consider the stability condition theta plus written like this. So this is but by definition this is 1 0 0 0. So this is regarded as a character of the quotient of G and delta modulo HK. So basically, all the entries except the first one is all 0. So this is regarded as a character of this. So this is atom to GLN. Okay. And we also call this group G prime. So then this modular space in theta plus A delta tilde is, by definition, this is the GIT quotient of rep A delta tilde modulo the action of G n delta tilde sorry G okay so D Gn delta with respect to the stability condition and because of the choice of theta plus, this is obtained as a two-step quotient. So rep A delta, the affine categorical quotient of HK, and then take the quotient by the remaining action of G prime with respect to the theta plus. Here, this theta plus is regarded as a character of G prime. Okay, so here we can apply this theorem. So in fact, the first quotient, affine quotient, is identified with the A prime 1n. So here A prime, so Q prime is the quiver that was used when we realized the Hilbert scheme of points on theta mod gamma. So this is the quiver like this. So one arrow from one to the other and 3 loops on the second vertex. And A prime is the path algebra. And then A prime is algebra. It is a quotient of the path algebra modulo the relations. So more precisely, so these relations are the commutator relations and be these two generated by these two relations. And the module is theta plus. So in order to apply this result to this one, so basically, in fact, we only in this case we only need the second type of generators. This needs some argument, but somehow we can show that we only need the second type generators. And in this case, the K is this subset. And as I mentioned earlier, the only cycles starting from this vertex is coming from the cycles on the right hand side. So, and also, basically all the cycles just starting from this vertex, how to say, all the functions associated to paths starting from these cycles are generated by, we only need 3 types of cycles, and in fact these 3 cycles correspond to the generators of in some sense these 3 cycles are the generators for the generators of this invariant ring in this case. So we need some argument to justify this statement. But in it, we can prove that this affine quotient is isomorphic to this representation space for this simplified quiver. And finally, so this stability condition in fact corresponds to the the third condition for please recall that in the definition, in the construction of the Hilbert scheme of points on AG singularity, there are three conditions. These are the first two conditions, and the third one corresponds to the surjectivity to the n-dimensional space. And in fact, the third condition is equivalent to the stability condition for this stability condition. So this is, so finally we can conclude that this is atomic to the Hilbert scheme of endpoints on C2 mod gamma. So in this way, we can prove the claims. So in this part, we need more argument, no, some we need more non-trivial argument. We need to, we can prove that using this theorem. Okay, so and finally, so so now we can prove that modular space is atomic to this Hilbert scheme. And originally, so we should show that the Hilbert scheme. So by that isomorphism, we obtain a closed immersion. And from the Hilbert scheme of points on C2 mod gamma. So this is isomorphic to the modular space for A delta tilde. And this is a closed subscheme of mu theta plus pi gamma tilde delta tilde. And we can prove that in fact this is an isomorphism. So by using the following two facts, this is theoretically surjective. This is again due to Gamelgard, Genge, and Chandroy. And also this modular space is reduced. This is also a non-trivial result due to Gahn and Ginsberg. In 2006. So we can conclude that this is an isomorphism. So this is a cold immersion and theoretically surjective. And we also know that the target is reduced. So we can conclude that this is an isomorphism. So in this way, we can prove that the Hilbert scheme of endpoints on C2 mod gamma is isomorphic to the Nakajima variety. So in particular, we can show that this is a normal variety, reduced and irreducible and normal. Okay. So it's almost time. So maybe I should stop here. Thank you very much.
Thank you very much for the interesting talk. So are there any questions? So if you are given any Q factorial terminalization of the symmetry power, so is it always a moduli space of for some theta stability condition theta
So the symmetric product of
of C2 mod gamma?
so, it's basically the symmetric product of theta mod gamma is so in this case every Q factorial terminalization is smooth.
Okay.
So yeah, so by the result of Bellamy and Crow, all the symplectic, like all Crepant Q factorial terminalizations are obtained as Nakajima varieties. They are all smooth.
Mhm. So is it true for arbitrary symplectic singularity or only for this singularity that
This is a very rare phenomenon. So
Mhm.
in general, usually we don't have symplectic resolutions. So
Mhm.
and yes, usually we can't expect that symplectic resolutions or Q factorial terminalizations are obtained as Kuiper varieties.
Mhm. So if a symplectic resolution exists, does it also imply that so any other Q factorial terminalization are also resolution or not necessary?
There's a general result due to Namikawa, which says that if the singularity, if the symplectic singularity admits one symplectic resolution, then any other Q factorial terminalizations are smooth.
Uh-huh.
So if you can find one symplectic resolution, then all other terminalizations are smooth.
Mhm. And also one last question. So about the reducedness of the Nakajima quiver variety. So for which kind of Nakajima quiver variety we know the reducedness?
Maybe this is the only, not only so. For generic stability conditions, basically quiver varieties are smooth, so in particular reduced. But so here we consider non-generic stability conditions. For non-generic stability conditions, the reduced is not clear. So I think it is usually difficult to prove the reducedness. So in this special case, this was proved by Kahn Ginsburg, but in general, it probably it's difficult to prove.
Yeah, I think in general it's still open.
Yeah, I think so.
Yeah. Okay, so are there more questions? Well, if there's no more question, then next thing's Rio again. So thank you very much. So we will have a second talk at so 3:30. And after the second talk, we plan to go dinner together. So if you didn't register and plan to come, so please come to see me. I will see whether there are still extra places. So if you want to come, then you will need to share the cost.